f of b minus f of a. That's what that meant. You take your b, you plug it in. Take your a, you plug it in, then you subtract it. Now, what we've been talking about this entire time is something called net signed area. I gave you net signed area before. What net signed area was this. You took the area 1, you took the area 3 because it was above the x-axis, and you subtracted area 2 because it was below. That is what your definite integral will do automatically. Without asking you, it will do that. Why does it do that? Well, because the area below counts as negative area for a definite integral. That's actually one of the things that we saw with our switching of signs. That's another reason why that comes out negative, is because when you go from whatever this point to whatever this point is, if it's below, it's going to be subtracting those areas and thereby causing them to be negative. So this counts against your total area. Now, in order to count total area, what you do is this. You say, I want to count up the area that's between the two curves. I don't care which one's on top or which one's on bottom. I want to find out the actual area between them. So find the area that's here and here and here. That would be total area. This is net signed area. So one question I have for you is, how in the world could we get this area to become positive? How would you do that?
Absolute value.
Say it louder.
Absolute value.
Absolute value will absolutely take any negative thing and make it positive whenever you see it. Right? So what we're going to try to do is this. We're going to try to take this one and flip it over and say, all right, well, total area then should become area 1, area 3, not that. We don't want that. That's going to count as negative area. What we want to do is find a way to flip it over here and make it count for us. That would be total area.
Would you just flip this?
For total area, we need to change the sign of area 2. In other words, if you kind of go on further than this, you say, well, I want to change the sign of any area that's below the x-axis. If I can do that, then that negative area actually counts as positive area, and we add it up together. And what we end up doing is we end up finding the area between two curves. One of the curves is the function, the other curve is simply the x-axis. Now, in section 5.1, we go further, and we actually do legit two curves, not just the x-axis. But keep in mind that this is exactly what we are doing, is finding the area between two curves. So I'm going to draw on this later. You understand? So this is one curve. This is the other curve. It's a very simple curve. It's just x equals 0. But what we're doing is finding the area that's bounded between two curves. That's what we're doing literally. In order to do that, that's positive, that's negative. We have to change the sign of that for the x-axis. That's the idea. So for total area, we need to change the sign of area 2, or in other words, the area of any piece of the region that is negative. In this context, excuse me, that's the area that's below the x-axis.
Are we saying we want FOT plus FOA?
No, I'll show you how to do it right now.
Oh.
Okay, now check it out. Here is net signed area. Net signed area said you start at A, you go to B, you just take the integral of whatever function you have, and whatever happens, happens. Positive area means most of it's above the x-axis. Negative area means most of it's below the x-axis. Even if we cross over, it just basically says your net change, what is mostly happening, whether you have more positive than negative or more negative than positive, no matter what it actually is on your graph. Does that make sense to you? Now, total area says, no, 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 no. We're going to take all the negatives and we're going to make them positives. What are we going to do with the positives? We're going to leave them alone. The thing that leaves positives alone and changes negatives to positives is, of course, absolute value, like you said. So total area says, all right, we're still going from A to B, but now we have the absolute value of f of x. Just remember one thing. The absolute value of f of x, or the absolute value of any function, is actually piecewise. So it's going to look kind of like this, is why we did this first. It says you keep f of x if f of x is positive. You make it negative f of x if f of x is negative. That's the way you do absolute value. It says, shoot, man. If your function's positive, why are you going to change it? That's going to be a positive area. In fact, we know it's going to be a positive area from one of the properties I taught you before. Whenever your function is completely above the x-axis, hopefully you're listening to this, whenever your function is completely above the x-axis, your area would be positive. You remember that? Whenever your function is completely below the x-axis, your area would be negative. If we make an area, a negative area, negative, that's changing the sign of your negative area, it will become positive. So here's what it says. This area will be positive. This area will be negative, so we're going to change the sign. It will be negative. This area become positive. So here's what it says. Negative, that's changing the sign of your negative area, it will become positive. So here's what it says. This area will be positive. This area will be negative, so we're going to change the sign, thereby making it positive. Are you clear on this? Did that blow your mind? Like a grenade? Did it really? Sweet, I hope so. Would you like to see an example in practice? Yeah. It's not hard. Not hard. It's going to look a lot like this, as a matter of fact. There's just one more step to be able to figure out where you separate it. You see, we just did this piecewise function, only in this piecewise function, I gave you the separating mark, right? I said you go from 0 to 2 and 2 to 6. All you're going to have to do is figure out where that mark is for yourself. What that's called is a sign analysis test. Bam! Told you this is exciting stuff here, folks. Sign analysis. How can you not get excited with sign analysis test? Find the area between f of x equals 1 minus x squared and the x-axis on 0, 2. Well, what we mean is total area. Let me insert that right here. Find total area. Total area between them. Because net signed area would be very easy. Net signed area, you would just take the integral. Look at, here would be net signed area. It would be from, where would your integral start, ladies and gentlemen? Where? Where would it end? Your function is?
1 minus x squared. Yes.
This right here is net signed area. Do you understand?
Mm-hmm.
It would take the area above the x-axis, subtract the area below the x-axis because it would be negative, and that would be your net gain, your net change in area. Okay, that's what that would be. This says, no, total area. The total area will do this. It will take the negative area, it will flip it above the x-axis, or at least it will change the sign of it, and that would count as positive area. It would say, I want to find the area between them, take all of it and add it all together. No matter what the sign is, add it together because the absolute value will change it to a positive. You following that? Okay, so how do we actually do it? Well, here's your steps. Step 1. You got to set your function equal to 0. Do you know why you got to set your function equal to 0? Not y-intercepts. Hey, if you're trying to figure out where the function is above and below the x-axis, you better find out where it crosses the x-axis. That makes sense to me. Does it make sense to you? Yes. If you know where it crosses the x-axis, then you can perform a sign analysis test, plug in some numbers easily and say, oh, it's above, it's below, therefore I know when the area is going to be positive, when it's going to be negative. You get me? Okay. So set the function equal to 0 and solve. So for us, I'll do that in purple so you see the work over here. We're just going to get 1 minus x squared equals 0. Well, there's only like 2 more steps. What are you going to do with this? Probably add x squared, yeah. And then you're going to?
Square root.
Yeah, sure. Square root plus or minus x equals negative 1 and 1. Raise your hand if you feel okay with this so far. Okay, now the next step. You got to set this up correctly. What you're going to do is you're going to do a sign analysis test. Sign analysis. But you only need a few of these points. What points do you need? Well, let's see. Do you need the 0? Yeah. Do you need the 2? Of course. Do you need the 1? Yes. Do you need the negative 1?
No.
No, you don't need that one. Why not?
It's not within constraints.
Don't even care. So really, you're gonna make a sign analysis with your endpoints of your interval, your bounds of integration, and whatever points fall between that. That's it. So make it with your endpoints and your x-intercept that fall within those endpoints.
No, so if you have no points of intersection within your bound, you just use your 2 endpoints.
Then you know what? You won't even need that. Because it's either all going to be positive or all going to be
So
negative.
you just test one and go with it.
Yeah. So sign analysis with endpoints and any x-intercepts that happen to be within your bounds of integration. Well, let's go ahead and do that now. So we're going to make a sign analysis test. Here's how sign analysis tests look in case you forgot. What you do is you take your bounds of integration first. The bounds of integration start at 0 and they end at 2. You take any of those x-intercepts that you have. Those are the places where you're crossing the x-axis, and therefore that's the places where your signs could possibly change. Well, only one of them. That's 1. Feel okay with your sign analysis so far? After that, after you make that number line, you just determine when f of x is above 0 and f of x is below 0. That's just plugging in a point. Plug in 1 point for each of these intervals. That's only 2. You don't have to go over here. I don't care. I don't care about that one either. I care about these 2 intervals. Plug in 1 point, see whether it's above or below the x-axis. Recall that if it's above the x-axis, the area has to be positive. If it's below the x-axis, the area will be negative. And this is the separating point between those 2 areas. That's why we set it equal to 0. So we're going to determine when f of x is greater than 0. That would be above the x-axis. Or less than 0, below the x-axis. Have you done it already? You plug in probably 1/2. Where are we plugging this in, by the way?
To our original function.
Yeah, plug in the function. It's going to tell you, I don't care about the number, I care about the sign of the number. Which one's 1/2?
Positive.
Okay, so this is positive and this one's negative? Cool. What this says is that from 0 to 1, I'm above the x-axis. From 1 to 2, I'm below the x-axis. We're going to have to come up with that sign change. We're going to do it right now. What we do is we're going to split up the integral using the definition for absolute value. Okay, here we go. This is a good part. Let's find total area. So where are we going to start and where are we going to stop for our first integral? Where are we going to start?
0 to 1.
0 to where?
1.
Cool. Yeah, absolutely. Now, think back to this. What the absolute value of x says, absolute value of f of x says is if it's positive, you leave it alone. If it's negative, you change the sign. So when this is positive, here's what we're going to do. Between 0 and 1, do I change the sign or not? What do you think? I'm going to leave it alone. I'm just going to do 1 minus x squared. Why don't we have the absolute value still? Absolutely not. I'm actually using the definition of absolute value. Right?
But because you don't need it, the absolute value of that, you're not changing the sign.
I'm actually using this to change it. I'm saying, well, if f of x is positive for that region, then I know the absolute value of f of x is simply f of x. I know that this is positive for this region, therefore the absolute value of f of x is simply f of x. That is what this says. It says, hey, if it's positive, you don't change anything about it. You basically just drop your absolute value signs. Are you with me on that? Okay, dx plus, again, the reason why we do this, just like the piecewise example, do you recall that between 0 and 2, if I find some intermediate point, I can split up my integral from 0 to 1, and then also from 1 to 2. You remember that? It's continuous, no problems, no breaks. That's great. Between 0 and 2, we're going to go 0 to 1. We're going to go 1 to 2. Now, between 1 to 2, this is why we did our sign analysis test, our function is negative, which says it's below the x-axis. It says if the absolute value of x, well, if f of x is negative, you're going to have to change that sign. You follow? You can't just drop the absolute value because it's not positive. You go, all right, well, back up here, I'm going to have 1 minus x squared, sure, but negative. If it makes you feel better, I can do this too. You can do lots of things as you want. Show of hands, how many will be okay with that so far? Okay, I'm not going to do much of a recap. I'm just going to say what we're doing here is basically using a sign analysis to our advantage to determine when a function is positive and negative. Where it is positive for that region, you leave it alone. You just write it, no absolute value. Where it's negative, you just write it, but you have the negative in front of it. This is the reason why, though, is because we have this scenario, because we know if the function's above the x-axis, the area will be positive. If the function's below the x-axis, it will be negative. And that one nice property that said if you have a continuous function between 2 points, you can split up that integral into 2 different integrals by using some number that's between them. That's all these properties coming together. There's a lot of properties we're actually using here to be able to do this. It's kind of cool. Now, what I would do with this integral, I wouldn't distribute this, I'd pull the negative out. I'd just pull the negative out, just make it a minus. That means that the area is 0 to 1 of 1 minus x squared dx minus 1 to 2, 1 minus x squared dx. I'm doing this just so you can see this part of it. Check it out. Look. You know this area is positive, right? Right? You know this area is going to be negative, right? Minus the negative area, that's adding the area. That's all this really does for you. Why don't you go ahead and do those? See what you get.
get
So close. Okay, let's see. Wait a minute. Oh. That was really close.
I got 2. I don't know if I did it right, I did it pretty quick. Did you get 2? If you didn't get 2, it's all fraction work, but hopefully you got 2. How many people were able to make it down to this part right there, that part, integral? Did you get that far? Good. Did you plug in all the numbers at least this far?
Yeah.
From here on out, it's just fraction work. Calculators are fine, I don't care, as long as you're able to get the right answer down here, be able to do that. Can someone please double check my work to make sure that I am correct on that?
Yeah.
Make sure all my signs are right. You did? How many double checks do I have that got 2? Good for you. Good for me, actually. I did it. Shoot, come on. All right, well, we're ready to tackle the fundamental theorem of calculus part 1. The first part we did was actually part 2. That was all the area things and being able to calculate a definite integral, which means an area, by doing that whole subtraction. Find the antiderivative, plug in b, find the antiderivative, plug in a, and subtract the 2. That's the fundamental theorem of calculus part 2. The part 1 basically says this. It says that derivatives and integrals are inverses. It says one undoes the other. That's basically the idea in the most common, small sense I can make it. So let's suppose we have this function, y equals f of x, is some function, and it's continuous over a certain interval. Starts at a point, and ends wherever we want. Ends at some x down the way. You get me on that? Some x, even changeables, provided it's continuous up to that point. Then the area is a of x. We already know that. Area is going to be some area function such that when I take the first derivative of my area, what does it have to give me in this case? Say it again. Very good. So if f of x is continuous over this, then the area is a of x, some area function, and the derivative of the area function must give me back my function, my original function. That was the antiderivative thing. Saying that this is the antiderivative of that, treating this like a derivative going backwards. Well, I could write that a different way. I could write that also as the area then should be the integral of f of x. We also had that from what we've been studying, right? It says that if I want to find the area, it should be the integral of f of x dx from a to x. You okay with that as well? It says that the first derivative of the area is going to give me my function back. Therefore, the antiderivative of my function between my two bounds, whatever they happen to be, should give me my actual area. Should give me the area. Now, this is in terms of not a b, but an x, so as to give me the a of x, not the actual area. Does that make sense? It'll be a function of the area. That's what it's saying there. How many will feel okay with that so far? Now I'm going to do one thing so that we don't get a little bit confused, because it's kind of awkward to have a function in terms of x and then have a bound of x. What we use here is called a dummy variable. It really doesn't matter. It's just a variable that we're going to be integrating because you're going to be plugging in x later anyway. So the x's will appear. So typically what people do at this point is they go, you know what, let's not call it f of x. Let's call it f of t dt. They make it a dummy variable. Now, why the dummy variable doesn't matter is because when you think about it, when you take the integral of this, you're going to have a function in terms of t, correct? But look at your bounds of integration. You're going to go from a to x. You'll be plugging in the x's somewhere for your t's. You'll reinsert them into your equation. That would give you an area function in terms of x like we're looking for. How many people feel okay with this so far? Okay. Well, here's the basic idea. I'm going to try to tie all this together for you real nice and neat. I'm going to try. I'm going to try. I really will try here to make it neat. Would you agree that this equals this? Yes?
Mhm.
For sure. You believe that?
Yeah.
Oh, then we're almost done. That's fantastic. Very good. Because this means a derivative, right? That means a derivative. So the first derivative equals f of x. The first derivative equals f of x. However, we also have this statement right here. What I'm going to do is make a little substitution right there. So what this says is the derivative of a of x here's another interpretation of a of x. What's it have to equal? What did this equal?
Yeah.
Are you seeing that this is the same thing as this? Yes or no? This is a of x, so is that, from right here. I just went this way. I made a of x that way. That has to equal f of x as well. This right here is the fundamental theorem of calculus part 1. Yeah, because we talked about this first.
And so where you have the f of t, because of the way you do the integral, you're just swapping it out and reinserting your x to make it come out with f of x, not f of t.
Right. We use the t here so you don't get confused an x with x, because it's hard to think about, oh, I'm going to plug an x in for an x. That's weird. Why do we do that? But so what we do is we use a t and say I'm plugging in both x and a for my t.
Or you could like use x subscript 1, x subscript 2 to keep them separated. Or does it matter what we use besides t?
No, you could use h there if you really want. T is a dummy variable. It doesn't really matter. You're going to be integrating some variables, right? For those variables, you'll be plugging in x's. That's the idea. Did you follow? A of x equals this. Derivative of a of x equals this. Therefore, derivative of this equals f of x. That's the fundamental theorem of calculus part 1. Here's what it says in plain English. It says, if you take a, what's this stand for? What's this stand for?
Integral.
It will give you back your
Function.
That's it. If you take a derivative of an integral, basically it undoes everything. It essentially says they're inverses. It says a derivative undoes an integral. An integral of your function gives you something, right? An area function, as it were. Then you take a derivative of that, gives you it right back. Gives you your original function back. Now, why is this important? Because that seems pretty common sense, doesn't it? I mean, we've already kind of thought that, well, I mean, shoot, if an integral is undoing a derivative, it should be the inverse of a derivative. This proves it, that a derivative is an inverse of an integral. But why we do it is because sometimes it makes certain integrals very easy to do. Here's why. Maybe not certain integrals, but certain computations very easy to do. Without doing any work, you can tell me what this is, actually. Say what?
T to the fourth.
Not t to the fourth,
X to
you're
the
very
fourth.
close. X to the fourth, without doing any work. Why? Well, because you have a derivative of an integral. The integral starts, I don't care, but it ends at x, wherever it is. That means that this is going to be whatever our dummy variable is, but with an x instead. So this becomes x to the fourth. By this theorem. By that theorem. If you want to see it proved out, which we can do that directly, I'll show it to you right now. That would be a derivative of, if you did the integral, you're going to get t to the fifth over 5 from 1 to x. True? What that would give you is a derivative of x to the fifth over 5 minus 1 to the fifth over 5. Do you see where the x is coming in? Do you see why we have a dummy variable? Doesn't really matter. You're plugging in x for it anyway. Okay. Do you see why this number doesn't matter? When you plug in a number to that, you're going to get all constants. What happens when you take a derivative of constants? 0. So really only that matters. So you're going to get a derivative x to the fifth over 5 minus 1/5. What's the derivative of x to the fifth over 5 minus 1/5, ladies and gentlemen? Which proves it. Well, at least for this example. I basically kind of proved it here with this statement here. It's done. There's some more serious proof to it if you really want, but that's basic enough for us. Now, that you could do directly. Some of them you can't. So when you get to this integral like this, I don't want you to spend too much time on it because there's no way you can do this integral in this particular class. Let's say you had something from 1 to x sine of t over t dt. You can't do that integral directly. You can't do it the same way I did it, all right? It's not, you can't just hammer at it. Not in your integration table, you can't do it. However, because you have a derivative of an integral from 1 to x, from a, any a, to x, you can use the same property right here. So how much is this going to be equal to? Sine x over x is right. That's exactly correct. Now, one thing, it does have to be defined for the entire, just like, remember how we found out last time, it's got to be defined. You can't, it's got to be continuous. It's got to be very nice. You can't have the undefined points. It has to be bound somewhere. Are we okay here? 1 to x. Remember, this is the small number, so it can't go backwards. Are we okay? What's the one number that's not okay? We miss a 0, so we're okay. If this had gone from like -1 to x, we'd probably have a problem because we couldn't evaluate that integral. Yeah, that's it. So when you get to some of your homework, some of it's going to be kind of easy. If it looks like this, a derivative of an integral, and you're going from a to x, and it's defined for that whole region, I mean, it starts higher than any problems that you have, that's all you got to do. Plug in your x's and you're done. A derivative will undo an integral. That's the fundamental theorem of calculus part 2.
Part 1.
Part 1. What'd I say?
2.
Part 1. That's it. Oh, people understood that. Good for you. That's fantastic.
Which all integrals are like that.
I know, right? Well, the thing is, we don't always take derivatives of integrals right next to each other. It's not, it doesn't happen very often, but it's a statement that says it is true. It's proving that they are inverses. Now, we're going to move on. This is typically a different section in most other books, but this book ties it all together with this. We're going to continue doing definite integrals, only we're going to do some more, I guess, tricky ones. They're not super tricky, but they're going to incorporate something you've already learned in this class, which I guess is kind of nice, but we haven't dealt with it yet. We're going to start talking about how to do definite integrals that might involve a substitution. You ready to learn how to do that? It's not hard. You've already learned substitution, right? So if you've already learned substitution, I just have to tell you what to do with the bounds of integration. After that, everything falls into place. So same idea. Let's look at how we deal with bounds. That'll be the rest of our lesson. Okay, so, what are we on? We're still on 4.5. This is still an extension of that. So we'll talk about definite integrals. But this time we might have some substitution. It's still in your best interest on your homework to check if you can do the integral without substitution. If it's just a simple distribution or a simple changing of some exponents from square roots into 1/2, I think we had one of those last time, right? And you combine them, that's probably easier than substitution because substitution might even work in that case. But if you have to use a substitution, at least you know how to do it already. There's basically two methods. I'll show you method 1 first, and I'll show you method 2. Method 1 says this. It says you're not going to change your bounds. You're going to do the same exact thing as before, but you're going to be sure to substitute back in for u before you evaluate. So method number 1 is don't change bounds, sub in for u at the end. Don't change the bounds. Substitute back in for u before you evaluate. And you'll see exactly what I mean on this example. There you go. Okay, let's look at the integral. This is the first time we've had like a, honest to goodness, integral with some numbers up there and something that wasn't just super basic. So this looks like a real integral with some real numbers and some honest work to do. First thing, could you distribute everything out? You could. You really could in this example. You probably wouldn't want to though, because that's a power 3. It's going to take you a long time. So substitution in this case would probably be your best bet. Ignore the bounds when you're picking your substitution. It's just a basic integral, just like you did with indefinite integrals. Pick the correct substitution. Why don't you do that now? At this point, I'm hoping that most of the substitutions are pretty obvious. The only times they maybe wouldn't be is with some of the square roots. Sometimes people forget about that. Or with trig functions. Sometimes they're not obvious. You have to guess and check. So, u. What's u? Good. What's du? Don't forget the dx. You need the dx. And then how I've taught you how to do this is I've had you solve for dx. That makes the substitution nice and neat. So solve for dx, you're going to get du over 2x equals dx. You okay with this so far? Everybody? Okay. Now what do we do? So we're going to have, what are we going to have? Why don't you tell me exactly?
4x,
Okay, I heard 4x. What'd you say after that?
u,
Perfect. And then what?
and then du over 2x
Excellent.
from 2 to 0.
We're going to talk about that in a second. Firstly, how many people feel okay with our substitution? 4x is still there for right now. The u cubed comes from u cubed dx. No, not dx anymore. Du over 2x. And then we start simplifying things. And then Michael said something interesting from 0 to 2. Yes and kind of no. Yes and no. We're going to put it there. But I want to show you why method 2 can do something different for you. Because as soon as you do this, from 0 to 2, as soon as you do that from 0 to 2, look what's going to happen. Sure, you're going to eliminate this 2, and that's going to become a 2, yeah? And you're going to eliminate this x and this x. And what you would get is 0 to 2 with a 2 out in front of it. Did you see where the 2 out in front of it's coming from? That 2 pull out front. U cubed du. Which variable? What's your variable? U. Yes, it's u. Not you, you. It's u. What were these bounds originally in? So we kind of have bounds that don't match our integral right now, which is sometimes leads to problems because what people do often is they'll do this. They'll go, okay, hey, I know how to take an integral. It's very easy. I'm going to have 2u to the 4th over 4, and then they do this. Explain to me why that might be incorrect.
Because in terms of
You haven't tested
x.
Right. These are in terms of x, right? But the integral makes it seem like you're plugging them in for u. Now, you can do it this way. You can. You really can. Provided that you do one thing. Provided that you don't change the bounds. We didn't change the bounds. And substitute back in for u before evaluating. So not here. This would be the wrong way to go. Do you see why it's the wrong way to go? Honestly, do you see it? You're trying to plug in x's for u's. That's not going to happen. So instead, we're going to do a little bit of simplification still. We're going to get u to the 4th over 2, and you all said that you're going to substitute back in for u in terms of x before you plug this in. You see, if these are in terms of x, I want my function to be in terms of x, my integral to be in terms of x, what I got to be in terms of x before I evaluate. So we'll substitute back in for the u. We'll get our x to the 2nd minus 1 all to the 4th power, then over 2, and at this point, this is where I should evaluate. So right here, it's a little bit cramped up there. Now we get to go from 0 to 2. That's okay. That says, now that we have this in terms of x, great. They match up with our x bounds that we started with. Now plug in the 2, plug in the 0. Why don't you do that and see what you get? Don't neglect that 0. 0 squared minus 1 isn't 0, so you're going to get something over there. I got that. Did you get that? Mm-hmm. Cool. What's it mean? It's an area. What type of an area is it? Total area or net signed area?
signed.
Good, we haven't talked about absolute value or anything. Not sure if that one's gonna have any negative area. If you graphed on a graphing calculator, you could tell. Or if you wanted to find out total area, what you would have to do is find out whether that's above or below the x-axis for all of those points. I'm not sure in either case. Maybe you can look at that. But you'd have the absolute value for total area. You remember doing that from last time? You had absolute value. You take this, you said equal to 0. You'd have your endpoints and any points in between there that would change the sign of that thing, and you separate those two intervals, and that's how you do that problem. So this actually is net signed area, whether or not we have it all above or below. And this, if it was all above the x-axis, net signed area would be total area. But if there's any area below the x-axis, it would have automatically subtracted in there for us. So that's the case. By the way, has anyone graphed that? Do you know if there is any area below the x-axis between 0 and 2? I guess we could find out real quick.
That whole function. Between 0 and 2, yes, there's negative. Yeah, there is. Between 0 and 1, it looks like.
This is negative?
Yeah.
Okay.
So it looks like, I mean, there's a little portion
Like
of
that?
just a little bit on the side 0, it looks like. Well,
Aha. See? You can see. Yeah, we have a little bit below the x-axis between 0 and 2, so that's going to be counted against our area right here. So this is actually total, not total area, this is net signed area. It's discounting the part between 0 and 1, and then we have from 1 to 2 that would actually be positive, but it's greater than the negative area. That's why we have a positive 40 out of that. How many feel okay with that so far? All right, cool. Would it be substantially harder to do that? Substantially harder to break them up? Not really. It's actually just a matter of separating our integral, going from 0 to 1 and having the negative in front of that, and then going from 1 to 2 and doing it just like we just did. You just plug in some different numbers. So it's not that much harder, just you have to do the integral twice. So I don't want to do that right here because we have to change bounds a lot in the next example, but that would be something to talk about. Are you okay with this first example? Do you understand the idea of not changing bounds? Basically the same exact thing you do for every example. You just don't change the bounds, you do the integral like you normally would, change it back into x like you normally would, and then plug the numbers in. That's the first method. Second method says, well, maybe not necessarily a quicker way. It's not quicker. Maybe we can just do it a different way. In either way, notice that you're going to be plugging these numbers in. You will be plugging in 0, and you will be plugging in 2. You're just going to do it at a different time. So we're going to talk about method 2. I'll show you how that works.
do you have a preference on which method?
I'll tell you which method to use on the test when I want you to use it. If I don't tell you a method, you do whatever method you want. Okay?
So we should learn both methods.
You must learn both methods. Yeah. Okay, method 2. Method 2 is you change bounds. You change bounds during your first substitution. If that's the case, here's what I'll give you like a little foreshadowing of what's going to happen. You're going to change your bounds from x's into terms of u using your substitution. If you change your bounds into terms of u, do you need to substitute back in at this point for x? No, because they'll be in terms of u. So if you do method 2, you change your bounds, and then you do not substitute back in before evaluation.
It's the same.
tell you what, let's do the same example. Can we do the same example? Just do it a different way. So you can see I'm not full of smoke here. It really does work out. I'm not here to reteach you how to do substitution. I've already taught you everything you need to know. Doesn't change, so that's nice. You'll still use the same substitutions no matter what. What I'm here to tell you is there's a slightly different way to do it. So if we pick the same substitution u is still x squared minus 1, and hey, du is still 2x dx, and sure enough, du over 2x is still going to equal dx. That doesn't change at all. You still okay with that? Here's the change. The change says, well, since we're substituting everything anyway, I mean, we're substituting this for u, this x part for u, and this x part for u, why not just do the bounds as well? Why don't we substitute those things for u as well? And here's how to do it. All right, well, that's a good idea, Mr. Leonard. Let's try. Well, here's the point. When you look at that, that says x is going to become 2. That says x is going to become 0. Why don't you find out what u would be when x becomes 2 and u becomes 0? And that's the question. Notice how we're actually doing that right here. We're plugging in 2. We're plugging in 0. It's just within the evaluation process. Here you just do it beforehand, so that when you get your bounds, it's in terms of u, so you don't have to do this step. You just go directly from here. It's basically, do you want to do the work beforehand, or do you want to do the work after? Doesn't matter, you're going to do the work either way. So it's really up to you. Now I'm going to make you learn both. I'm going to tell you what to do, but it's an option for you. You got it? Okay. So we'll say if x equals 2 and if x equals 0, this is the whole process of changing bounds. If x equals 2, then u equals 2 squared minus 1. Then u equals 2 squared minus 1. See where the 2 is coming from, right? And u is going to equal what? 3. Okay. If x equals 0, u equals 0 squared minus 1. Very good. Well, now we can make a substitution with everything, and the bounds will match the variable, which is nice. So let's do it. Do we still have the 4x? Of course. Do we still have x squared minus 1? Of course not. That was our u. Notice how it's going to look exactly the same as the previous problem. du over 2x. The only thing that's going to be different is what?
Our bounds.
What did the 0 become? What did the 2 become? 3. It's going to be done the same way. 2 is gone. X is gone. So -1 to 3 will still pull the 2 outside. U to the 3rd du. Hey, we even do the integral the same way. We're going to get 2 u to the 4th over 4. And we'll simplify that. U to the 4th over 2. But now when I do my evaluation, do I have to substitute back in for the u? No, because we did our bounds. And that's the only reason why we had to here, because the bounds were in terms of x. Here you've already changed them. You've taken x's and you made u's out of them. Once you make u's out of them, you can use it right here. Get it? You can use it here. -1 to 3. Because those are in terms of u. Plug them in, you're going to get the same answer. So let's try that. Hopefully you get the same answer. It makes it so your evaluation is just a little bit simpler, by the way, because you typically, because you have this function's gone right now. You don't have to plug that in and then do all the math. Basically, you just do it ahead of time. You're still doing it though. You're still doing it. It's just kind of set aside for you up here, which is, I suppose, nice. Minus -1 to the 4th over 2. Well, what that's going to be is 81 over 2 minus 1/2. And again, that's 40. Show of hands, how many people feel okay about both methods? How many people prefer method 1? Method 1. Okay, that's cool. You can. It's fine. How many people prefer method 2? People seem to like that a little bit better for some reason. Simply because you're doing the work ahead of time, you don't have to worry about this later on. The two mistakes I see are this. I see, because the integration is not that bad, I see people making mistakes here. They either forget to substitute back in x here, or they accidentally do it here again, and they get something way off. You see what I'm saying? That's where the mistakes happen. So do one or the other. Now, of course, on a test, I will ask you for both. Maybe not even that one. I'll say do this if you want, but I'll give you some where you have to change bounds. I say I want to see you changing bounds. So you do need to learn that method either way.
So for those intermediate steps though, would you have to use a different notation than method 1? Since like where it says 2 times the integral of u cubed between 0 and 2, that's not actually true, right?
This is slightly off.
Right. So
Yeah.
how would you actually write that if you were?
You'd still write it.
Okay.
You'd lie. Yeah, you'd still write it. But this is one of the reasons why we have that. Because you go, oh, these bounds don't really match up with that letter. Now, you could say, well, maybe we'll just treat it like a dummy variable. It's really not because it's substitution. But we know in our head that we're just going to plug back in for x. So it still works. But those really don't match up all that well. Because they actually at all. They're x's and that's a u. Good question. Any other questions before we go on?
So then as a method.
It has to do the same thing. It is the same thing. You're just doing one part here, and you're doing one part here. One part before evaluation, before even integral, and another part after integral during evaluation. That's really it. You're doing the same work. Same work. Just two different places. Good questions. Any other questions before we go on?
Why does that work when you change the range of the bounds?
Why does it work?
Yeah.
Well, it's taking a function and make it something else, basically translating.
Into a different variable.
Yeah. And then you have to change your x variable into your u variable to make it work.
Oh,
Okay. So right now this is 0 and 2, but it's regarding the x function. This is -1 to 3, but it's regarding the u function that you just created.
Does that mean that the integral that we're translating into isn't within that family of integrals? Is that why it comes out to be the same area?
Oh, that's a good question. You're completely changing the function when you do this.
Right.
You really are. And so you're just making, it's almost magical that it works, kind of cool.
Yeah.
But you're making a different function and saying the areas will be the same because I'm working with different bounds in that function. If you try to do it graphically, I have a hard time believing that 2u cubed is going to look anything like 4x x squared minus 1 to the third. In fact, I know that because a cubic just goes like this, right? 4x x squared minus 1 to the third does, well, we saw it. I showed you the graph. It doesn't look the same. So you're changing functions, but you're only talking about the areas. So basically you're saying the area here between these bounds is the same as the area here between these bounds.
It's kind of like doing a ratio.
I suppose, perhaps, but it's a direct rate.
Yeah.
I mean, it's equal. Maybe proportion would be a better way to make an analogy there. But something similar to that idea. It's very cool. Now, you need to know that substitution doesn't always work, right? So you can't always do this. It's only very special cases. I can give you lots of integrals where you can't use a substitution. In fact, most you can't use a substitution with. That's special. Every one that you can do a substitution with, the derivative has to be in there somewhere, right? It's got to work that way.
Are we going to deal with the integrals John's, that we can't use substitution for
Not in this class.
That's next semester.
In your next semester, which I'll be teaching in fall, no, spring of '03. A year from now. So just go ahead and fail this class or something. Take it next semester, pass it with some other teacher. And come see me.
You're going to pay for being more serious. Just for
My videos won't be in order. See, this wouldn't work. They're going to be in order. All right, what do you say we practice a couple more? Would you like that?